Hello, I'm audible. Hi, good afternoon, everyone. We shall be starting in just 2 to 3 minutes. Hi, so I think we should start this session. Meanwhile, others can join in. Okay, so I'm just sharing my screen. Anyone can let me know if the screen is visible or not. Hmm, 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 hmm. Okay. Yes, I hope I am audible. So, without getting much delayed, just let us start this session. So, good afternoon, everyone. This side Ayush. I am a business development manager at Integrated Microsystem. In this particular presentation and the live demonstration of Synopsys Simpleware software, we shall be exploring how to optimize preclinical research using the tool. Why we have chosen this topic is because even one that is working with image processing has been using the basics of segmentation methods like threshold based segmentation or even a normal auto segmentation. But still, there are some challenges that we face with both CT data sets as well as MRI data sets. We have the foremost issue of noise generation. So there are a lot of noises that are being present in the data set that generally tends not to go away when we are doing the segmentation, and which may cause delay in doing the segmentation and various other issues. So in this presentation, I shall be just overviewing all the particular features that we have pre-existing in Simpleware, which can enhance our segmentation methods. Apart from that, just for the audience who hasn't used Simpleware or who hasn't worked with the image processing in past, I shall be just briefing out what the image processing basically stands for and how we are utilizing it in Simpleware. So without much delay, a brief introduction about our company. So we have been distributing EDA tools for over 20 plus years across India. We have multiple softwares under us. So all the Synopsys EDA tools like Quantum ATK, CentOS TCAD, front-end, back-end custom design tools. Apart from that, we also have Synopsys Simpleware software, which we shall be focusing in this particular session. We have customer bases across India over NITs, IITs, AIMS, DRDOs, government lab. So we have a good set of customer range, and we are catering them with technical support as well as any type of sales support, whichever is required. So without getting much delayed, let us start with what is actually 3D image analysis and why it is used for preclinical research. So many of you might not be aware about TICOM dataset who haven't used it. So TICOM dataset is nothing but, for example, if we are clicking our own picture through our iPhone, through our Android phone, so what we get is a 2D image of ourselves. So it's a 2D replication of whatever the camera is seeing. So this is how a normal image works. What if anyone who is working in a 3D based modeling, 3D printing, he wants to generate a 3D model out of that? So it's not that possible until and unless we have the depth. So we might be having the x-axis and y-axis of the particular images. We might be having the pixelated volume of the particular images. But still, it is consisting of many pixels, and we are formulating a 2D image of the same. And we are viewing that particular 2D image in a 3D view, which we use our eyes for. So how to basically develop any 3D printable model, how to basically do any sort of 3D image processing, that has various aspects. So the first one, when we are dealing with medical image dataset, is the DICOM dataset. That generally comprises of the MRIs, CTs, and micro CTs. When we are dealing with any medical image dataset, whenever we are working with such images, the first and foremost issue is the issue of artifacts or the poor contrast that we have in the particular images. To solve that out, we may need to use various pre-processing filters. We may need to use recursive Gaussian filters to remove out the noises or to at least reduce out the noises so that we can have a proper visualization of the data set. Apart from that, there is one term called volume rendering. So since I discussed just now about how a 2D image is captured and is captured in the value called pixels. When we are considering a 3D image processing, we are not just limited to pixels. We also focus on voxel count. What is a voxel? Is basically volumetric quantity of pixels. So it also has the z-axis along that. So whenever we are formulating a particular image, let me show with a pen. So enter options. Yeah. For example, earlier, if we are having a particular singulated image, it may be considering of n number of pixels. So one pixel here, then one pixel here, then one pixel here. So sorry for the drawing, but it's just a freehand. So like this particular image may be considering of many pixels. But when we are dealing with a voxel count, so we also have a 3D visual representation, like what we used to study in our school times, what's the difference between a regular rectangle and a cuboid. So small blocks of cuboids forms the particular voxel counts of the particular image that we need to work in the 3D. So this way we can get an actual representation while we are analyzing the depth. This is foremost important while we need to do any sort of 3D image reconstruction. For that, what we deal is the slices or the stack of images, to be termed in a general terms. So what's a stack of images is whenever we are doing the sort of segmentation, generally if we are doing a single set of image segmentation, so we will be having a 2D image analysis out of that. But if we are having a stack of images, that is multiple images aligned in a singulated view, so we can do the 3D volume consideration. And apart from that, Simpleware software also has the 4D image dataset support. So even if the particular dataset is having a time offset value, that too can be segmented out across the time frames. And once the segmentation is done, we can easily visualize the results corresponding to any time frame that is required for. Apart from this, we are also given with robust measurement and statistic to do any sort of quantitative analysis. For example, doing a point-to-point analysis, taking the consideration of a femur bone. If we need to do a lengthwise analysis of the measurement to be done, so we can select the particular point, and this way we can do the particular measurement whichever is required. Apart from this, we can do angle measurement. Then one more term, whoever is familiar with the 3D printing may be undergoing is volume thickness. So to do the 3D printing, we require a threshold value to be having on the surface for it to be printed. So we can also do the particular wall thickness calculation. Then working on any surfaces, we might need to clip that. Clip means, for example, if we have a 280 slice image data set and we need to clip around 140, so it will split up the data set into two equivalent parts, and then the particular two parts that have been segmented and splitted up can be later on used for doing the 3D printing. So this way multiple options are being catered using the 3D image analysis. Now, what's a basic workflow in 3D image analysis for specifically medical images in preclinical studies is, first of all, we take a basic CT and MRI dataset. Once the dataset has been taken, we check whether the particular dataset is having proper brightness or contrast or not. Once it is done, it's satisfying of value. We move on to the next part, being the segmentation. The segmentation in Simpleware are majorly of three types: manual segmentation, semi-automated segmentation, and fully automated segmentation. Considering the term fully automated segmentation, it might not always be advisable to consider for the fully automated segmentation, but still it can be used to just get a common landmarking of where the particular area is lying. If we are initially beginners with the software, we don't have a great knowledge of anatomy, so we can definitely use the automated segmentation, and we can have a general overview where the exact point is lying. And once we are familiar, we can use the auto segmentation and later on refine out the results using the manual segmentation tool like Smart Paint, Region Growing, then Background Flood Fill, which are various tools that are present in Simpleware. Then the next part is the model generation. Once the segmentation is completed, we are given with multiple options to generate models. So starting up with a surface model to be used for a 3D printing operation, so we can export out the file in STL, stereolithography, or 3MF, that is 3D manufacturing files for doing the 3D printing. Then we have the ANSYS surface support, Abacus surface to be supported out, then COMSOL, VTK, MATLAB, VRML, you name the export format that is required, and we do have the support in Simpleware. Apart from this, considering the model generation, since we don't have the analysis capability as of now in the software, but we have a good integration between the different range of tools. So we can do is we can create a FE model to be created directly in Simpleware, which can be further simulated in ANSYS software. So we have a good streamlined for that in our tool range in Simpleware. Then once it is done, we also support various types of analysis and reporting. For example, if we need to do a bone porosity analysis, that can be carried out. A particle analysis can be carried out. If one is dealing with a material data set, so fiber analysis can also be carried out. So there are multiple sectors in which the particular Simpleware software can be used for considering the 3D image processing. Now, just to give a brief overview how a multi-scale modeling looks like. So whenever we are dealing with a CT dataset or an MRI dataset, even considering a particular heart CT dataset, for example, so it's not like that it will only have the particular heart to be visualized in the dataset. It would be having the nearby regions. It would also be having the rib cage that is surrounding the heart, all the nearby bones, all the vessels that are that are present in the dataset. But what we have is we have the method of segmenting each and every part out. So what we call is we call it as Hounsfield unit, that is used to segregate out one part from another. In engineering terms, it is called as a grayscale value. So if you are quite familiar with the bit images, so every bit of images has some sort of grayscale value connected to it. For example, 8-bit image will be having a grayscale value of around 0 to 65535. Then a normal image would be having a grayscale value. For example, a CT dataset generally has the uppermost value around 3071. So these are the different values that are associated. That helps us in doing the particular segmentation for any implant that is present in the CT dataset can also be segregated out on the basis of grayscale value. So this is called the multi-scale modeling, where within the single CT dataset, we can basically differentiate out different anatomical structures that are present at different resolutions. We can modify, we can change the particular brightness and contrast and visualize the particular dataset, whichever is desired for our workflow. Now, there are 3 skills in general modeling. So what we have in Simpleware is we have the support of macro scale and micro scale modeling in Simpleware. So we have the support of CT and micro CTs. For the nano scale, we don't have direct support, but if someone needs to do a 2D image analysis at a nano level, and it has he has the particular TIFF image dataset, so that too can be done. But considering the macro scale, so we can have full anatomical structure on device. Any STL or CAD file that we are having, we can bring that down in Simpleware. We can do perform the segmentation or any other operation. For example, in STL file, if we are required to generate an internal lattice structure to reduce out the weight, that can be carried out. For doing a tissue-based modeling or material grain-based modeling, that too can be carried out at a micro level. So these are different scales over which we can further scale out how the modeling looks like. Now, what's the need of high-end segmentation software? So there are multiple softwares that are available, but why is there exactly the need of such software? Because whenever we are, since this webinar is specifically focused on optimizing preclinical studies, whenever we are having large number of data set, we need to have certain algorithms that are refined in such a way that we can deal with large number of data set in a short frame of time. And once we are working with such data set, what we can do is we can apply various sets of algorithms like auto segmentation algorithm, wherein it reduces out the time. I have such example in which a heart CT was taken and it took approximately 2 hours, 1.5 to 2 hours to do the manual segmentation, and the same task got completed using the auto segmentation in 2 minutes. Although some manual refinements were required, still the model was generated within 15 to 20 minutes. So the time you can see is very considerable. Apart from this, the optimization in the software, there are new tools that are being included on daily to daily basis. Then we have a streamlined 3D printing workflow support in any commercial software. Then we have the a particular FE modeling, FE simulation support from Simpleware to directly ANSYS Abacus. So these are all the particular advantages that we have while whenever we are using a high-end segmentation software. Now, what's the use of Synopsys Simpleware? So Synopsys Simpleware has AI-enabled segmentation tools. It has certain optimization algorithm in which we can directly reduce out the noises that are being present in the data set. This you can see a sacrum example right in front of us, where what we generally do is we had done a normal threshold-based segmentation. We have selected out the threshold range that was, I think, for this data taken around 200 to 3071. And once this segmentation was done, we segregated different parts. So this was a whole pelvis CT segmentation that was carried out. Later on, it was split into left, right femur, left, right hip, and sacrum. And for example, if we need to focus on sacrum, so we can check over here, the segmentation quality was not that great. So let me zoom in. Yeah. So you can see there are still a lot of cavities and gaps that were present. So how this simpleware helped us in further increasing the quality of this particular bone data set is we used a bone filling operation, and that is AI-enabled bone filling. So it takes the nearby grayscale value in mind and automatically solidifies the bone for us. And once it is done, we get a very accurate and a 3D representable structure of the particular bone that can be further be put on the volume rendering of the data set to check for its accuracy. And here we can also see the difference in the control levels in both the 2D view as well as the same changes can be carried out in the 3D view. So these sort of AI-enabled tools that are integrated in Simpleware apart from auto segmentation plays a crucial role while we are doing any sort of segmentation. Now, how to identify different parts in the image processing is one of the foremost important things. So whenever we are considering a MRI data set, we can generally prefer for a soft tissue segmentation. Whenever we are considering a CT data set, we can prefer for any orthopedics data set to be segmented out. Then what are the basics of medical image segmentation? So the first and foremost part is to do, if we are using a semi-automated approaches, to identify the region using a thresholding based approach. In Simpleware, we are further given the thresholding into three parts, that is on the profile line tool, the other one being a histogram, and a normal uh, uh, threshold tool in which we have the automated CT presets to be given out that can be directly used to do the segmentation. Once it is done, even after segmentation, some parts may be missing because it may have a different contrast level, but still may be a part of the existing data set. So for that tools, we can use a region growing based tool to automatically merge the different regions that I'll further show in the live demonstration, how to basically overcome the challenges that we face. I'm moving fast for this particular slides because these are the basics of image segmentation, and we need to work on how to optimize the particular workflow that we are initially having. Then the challenges that we face are noises that are being present in data set and partial volume effects that are being present. And the last but not the least is the complex anatomy, because we can't identify each and every structure if the particular image based quality is not very clear. And to do that, we need to have a great knowledge about the whatever threshold range that we are working for. Then, as explained in the earlier slide, the different sets of image modalities. So we have the CT support. So best for identifying the bone and high density materials. Then we have the X-ray, that is a 2D view of whatever image reconstruction that we need to see. And coming on to this X-ray only, we have a virtual X-ray generation. So even if we are providing a CT data set, we can generate out a virtual X-ray of any data set in all the particular views, coronal, sagittal, or axial. We can also have the orientation label to be put in. So there are multiple options that we can have. Then we have the MRI, then we have the positron emission transmission scan. So PET scan is also there. Then magnetic resonance imaging is also there. MRI is there. MRI is there. So we can easily identify different soft tissues or any other anatomical parts that is being present. So whenever we are doing the segmentation, the first and foremost important part is to import the DICOM images, to import any TIFF or raw image data set that we are doing. Then we can use various sets of operation to do the segmentation. In this particular case that is shown, we had used a spine auto CT segmentation, where it has segmented out the particular spine data into vertebrae and sacrum, renaming it as V1, V2, V3, V4, up to all the way to the sacrum part. and we can isolate each and every part. So for example, if we are working on lumbar spine, so we can just identify that part out, isolate it, and work on that specifically. Then comes the one of the most important trick or technique that we can use while we are doing the particular image segmentation. For example, this data that we can see had lot of noises. It was a CBCT data set that we had worked on. It had a lot of noises being present in this data set. So what we had done is we had gone to a smoothing filter option. So here we have the smoothing filter. Once we enter the smoothing filter, we have an option of recursive Gaussian. Here the target was selected as DICOM since this was earlier to the mask that was generated. And once we have selected a recursive Gaussian, the pixelated value that we selected is generally from 1 to 3. So in this case, we had selected our 2 value, and once it is done, we can see how precisely it had removed out the noises that were being present in the dataset. And here we were not able to identify the structure as efficient as we were able to identify directly in the volume rendering itself using our recursive Gaussians. This is one such method that can be used to remove out the filters. Then we also have various advanced tools. So we have a multi-level ortho segmentation to automatically segment out anatomy in the basic version of ScanIP itself. So here we have multi-level ortho segmentation, wherein we just set the number of masks over which we need to divide the DICOM data set for, and it will carry out a good segmentation for us. Apart from that, there are other advanced filters such as MRI bias field correction and for MRI data set that can be used. Then we also have various noise and removal filter in the advanced filter options. So multiple filtering options are being present. And to learn about each and every tool, we have a dedicated guide. So whenever we are working on any tool, we can see there is a question mark sign. So this question, whenever we will click on this question mark sign, it will redirect us to the specific tool in the tutorial guide, how we can access the tool, how we can use the tool for our set of workflow. So these are some of the basic noise reduction techniques that we can use to reduce out the noises and have a better structure to be visualized for directly in the volume rendering, and thus helps us in doing the segmentation. Now, coming on to the segmentation fundamentals. So this is in short the whole segmentation workflow that we can use in Simpleware software range. Starting up with the paint tool, here we start with the basics of segmentation. We can mark a specific region in one view. We can select the number of slices from, for example, if it's a 250 sliced image dataset and we need to do the painting in, for example, coronal view from around 40 to 60 number of slices. So what we'll do is we'll select a number of slices, 40 initial slice and final slice is 60, and we can just paint out the region whichever is required. A better approach is always to go with a paint with threshold. So here we can select out a threshold range over which we need to do the paint, and then we can paint out the region. The paint tool works as simple as how we can relate is everyone might have used MS Paint at one point of the time. So it works in a similar way. Whichever region that is required, we can just highlight that out directly in the 3D view or the 2D view that we are working on. Then we have a Smart Paint tool. So it works whenever we have already created a mask and we need to refine out that particular mask. So in that case, a Smart Paint tool can be used, which gives us both the option either to unpaint or to paint the particular regions on the basis of grayscale value. So it works on a watershed algorithm, and behind that it uses the standard deviation of the grayscale range. So whenever we are carrying out the segmentation, it will take the standard deviation of the particular grayscale range that we are working on, and once it is done, we can set out the percentage of value. So for example, if we are writing in a 0.63, so it will take 63% of the nearby grayscale range and do the smart paint to painting for us. Then we have a normal threshold based approach, which has the 3 methods: histogram based method, profile line, and CT presets. In background flood fill, we are given with another 2 sets. So we have a seed point option, or we can directly set out the particular threshold range. So a seed point option is very much preferable while we are working with any tumor case or any soft tissue case that can be used. Then we have a mass flood fill approach when we need to remove any disconnected islands that are present, which might be causing distortion in dataset. So in that case, a mass flood fill can be used. Then we have the 3D editing options, where we can use various various filters like a delete filter, then we have the particular smoothing, local surface correction, erode, then close, then open. So there are multiple options that we can use it. Then we have the auto segmentation tab that fully works on the auto segmentation principle in Simpleware. We have AI ML based pre-trained dataset that the software is trained on, and we can easily identify any region using this auto segmentation. And to support our own set of segmentation algorithm that is present in market, like a total segmenter from 3D slicer or Monai based model from NVIDIA, we also do have that integration in form of external models. So here when we can import any external model, even if we are creating our own sets of APIs and we need to integrate it in Simpleware, so that too can be done with the external model option in Simpleware. Now, first and foremost thing that many of our users ask, what's the basic difference between a manual and AI-based segmentation? So whenever we will be using a manual-based segmentation, it would be time-consuming because we need to manually remove each and every artifacts that are being present. Then we also need to see whether the particular area that we are marking up is properly marked in the particular 2D view or not. So to basically eliminate that, we have the AI based segmentation, but that too we generally prefer. Then even after you are using the automated segmentation, you need to check the accuracy, whether it's fully occupying the particular mask or not. So that can be done by overlapping it with the volume rendering of the data set that is used. There's no such thing like manual versus AI segmentation, to be honest. It's how we can integrate the manual with the AI segmentation, because if we are creating a competition that manual segmentation is better or AI based segmentation is better, so it's just a false narrative. What we need to focus in, how we can use the AI enabled segmentation method to enhance our manual workflows and ultimately reduce out the particular time of segmentation and having the best accurate models to be generated out. Then checking out some of the application in biomedical. So this is one such application. So for doing a pre-surgical planning, this particular patient had a VST defect, a particular model was printed, the segmentation was carried out in Simpleware. It was a 4-sectional model that was done. Here we can easily highlight a particular VST defect to be observed, and once this particular structure is generated, the doctor can plan the surgery accordingly. So these are the some of the application area. Apart from this, in doing any sort of pre-surgical planning to, for example, checking out the surgical cutting guides that are being created or any surgical guide that we are using, that can be cross-verified in a virtual environment. Then if we need to check the fit of custom implants over the anatomical data before the final surgery is performed, so that too can be carried out, or we can directly bring in the STL file of the implant, and once the particular STL file has been brought in, what we generally have is we can do the particular implant positioning in Simpleware, and once the positioning has been completed, we can have the particular best fit outcome for any data set, and it's proven in various publications that have used the same set of approach. Then one more thing is the simulation integration. So as explained earlier, that we have the FE and CFD based modeling software. But whenever we are doing FE based modeling or CFD based modeling, the next thing that is required is to export the model. Ultimate aim is to generate out analytical results of the same. So that can be done. We can directly export out the particular file as INP file, CDB file, or any export format that is required, COMSOL file, MPH, XT. So there are multiple formats that are supported. So we can directly export out the file, we can do the analysis, and again bring that result back in Simpleware to have further visualization, or if we need to do certain mapping, if we need to do surface deviation calculation to check for wear and tear of implant over a period of time. So that too can be done using this integration. So now coming on with how to import any CT and MRI dataset. So it's very easy. We have two sets of options. The first one being a scan folder option, and the other one being an open DICOM directory. So if we are basically using a CD dataset directly from CD, so we can select this open DICOM directory, and it will select all the particular series of dataset that is being present. We are working on a specific series of dataset. If we need to analyze that only, in that case, we can use the scan folder one. Whenever we will be obtaining the data set, we will be getting a preview. We also have advanced import options that I'll further showcasing in the live demonstration. And at the right hand side, we have the DICOM text. So all the specific patient information is being captured over here. The study type, patient name, then physician who has referred for the particular planning. So these all can be captured from the right hand side. Once it is done, we have a very simple segmentation workflow. It comprises in the image processing block. As shown earlier, we have the threshold-based approach. In threshold, we have the three modes, a histogram, profile line, and the CT preset that can be used for. And in this particular case, a histogram is used. So the uppermost grayscale value in this particular ankle CT segmentation, foot segmentation was around 1934 and the lowermost was around -3000. But our region of interest lied between 189 to 1934, that was the orthopedic part that we were interested in. So this is how a multi-scale modeling works. So nearby muscular region may be lying in this particular grayscale range, then the skin region might be lying, then a grayscale, then the skin might be lying in this grayscale window. So there are multiple windows and each peak represents a shift in the particular grayscale range. So this way we can easily identify and distinguish the segmentation which is to be performed. Now, once we have generated a particular segmentation using auto segmentation, we will be getting this tab of whichever parts have been identified. And once we have detected the particular parts, we can observe the same in the data set viewer. This is a eye sign that we can see, so we can isolate each and every part out. Then we can toggle the visibility of any part that we are working. So there are multiple options that can be used for. Then we have this thresholding and filtering options. So histogram analysis can be performed, and a profile line tool is done. So profile line tool is, for example, if we are considering this point, and this point, and we need to what we just let me zoom in a particular slide. For example, we are considering these 2 points, and we whenever we will select these two particular points, so it will show us the histogram range of the grayscale variation between this point and this point. And once this is done, so for example, this being A point and this being a B point, so the variation between A to B can be visualized in the histogram in a profile line tool. And this way, when we are working on any, for example, nerves, to identify any nerves or any vessel, that can be easily identified for. So this way, generating mask tool works and the threshold and filtering works. Then one more important tool, whenever we are working with any surface, if we need to impose any text, so that can be done. So we have both options, either to impose text or depose text. Then if we need to move the particular part, for example, if we are doing a femoral analysis and we need to rotate tibia across femur at angles 0, 3, and then 6, 9, 12, 15, 18. So that can be done using this surface tool option. We can rotate it, we can manipulate it in any direction that is being desired for. Then whenever we are doing a particular IFE modeling, we can mesh it out around whichever coarseness is required for. We can export that out for ANSYS Abacus to do the simulation. And once it is done, we can generally produce out our results. So let us now continue to the live demonstration of the software. Meanwhile, if anyone has any queries till now, please let me know. I shall be directly starting the live demonstration. And even in between the demonstration, if anyone has any queries, they can let me know. Sorry. I see no queries in the chat box. So let me open the particular software. So this is how Simpleware research tool looks like. It takes hardly 10 to 15 seconds to basically open the software. Once the software is opened, just for the beginners, this is the project information tab, where we carry out the particular information of the image extent, the spacing, the image extent, the volume the image is occupying, the memory size it is occupying. And here we have the new project from tab. So if we are obtaining a DICOM image dataset, we can obtain it from here. That was shown in the presentation. We can scan the folder and we can import the dataset. Then if we are working on non-destructive image analysis, ND, that is majorly used for material reverse engineering, that too can be carried out Then we have the PEC server connectivity. So for safer transfer between the hospital dataset, PEC server can also be integrated. We also have the stack and raw images, so any JPG, PNG, TIFF, BMP, any format that we need to import in the file, we have the supported for. And here we can also set out the spacing according to our specific requirement. One more important thing that even the old users of Simpleware miss is the advanced import options and what are its capabilities. So I'll just showcase how we can use that in our DICOM images. Before that, we also have 3D image format support. So HDR file, HPM file, then interfile analyze. All the particular files are being supported. We can import the file in any of the format, any STL-CAD, STL-PLY, IGS step. All the particular files can be plotted in Simpleware. Now, carrying on the basic segmentation, so I'll just select out any diagram. It may be containing a number of series. I don't know exactly what are the contents in the diagram, but we shall see. Uh, it takes, depending on dataset to dataset, if it's carrying large number of series, so it may take around uh, 30 seconds to 1 minute for the data to be loaded. If it's only having a single series or dataset, it may be loaded in 10 to 20 seconds. Just give me a second. So it will take some more seconds for the data set to be loaded. Once it is loaded, we will get all the particular DICOM tags information over here. Here to keep the anonymity of the data set, keep the confidentiality in mind, we need to anonymize the DICOM data tags that can be done from here. Once it is done, we can either use the advanced import options, wherein we can change the image dataset type. Further, if we need to do the resampling, sorry. So further, if we need to do the resampling, that too can be done. And once this all has been carried out, we just need to click on finish and it will load our dataset. In the advanced import options, there is one more feature. For example, if we are working on any specific bone part, so we can select a particular presets value and we can later on work on the specific part. So this particular DICOM data tag, why it was taking so much time is it had multiple data sets present in this folder. So it had a pelvis data set that has 280 slices. So it has 279 slices in total. Then a femoral sample that has 300 slices. So slices are the stack of images that it is occupying here. We can see. Then it also has a CT and geo data set, the CT data set that we are having. And this is the particular time offset data set that we see. Here, whatever image information that we need to see, we can check from here. We can anonymize the particular DICOM data text from here. And we can also go into advanced import options and we can select out a particular image data set type. For example, when we will be using an 8-bit unsigned integer, we can also check for the presets. Here we can check out the different presets to be selected out and we can have a better visualization of whatever result that we are working. Once we will click on finish and it will load out the result. If we need to use whole DICOM data set range, so we can again assign that to unsigned integer or 16-bit signed integer, whichever data set is required. Here we can directly crop the particular region before even we have imported it in the Simpleware. This will further, if it's a large data set, if it's requiring huge memory to be allocated. So this way less memory could be used for. I'm just loading a particular 4D image data set. So we'll have a clarity how a 4D image segmentation looks like and how to basically work on any 4D image data set. Because if we are familiar with the 4D image data set, we can easily do the 3D image segmentation because it's almost the same, whichever process that we are repeating for. So this is how a 4D image data set looks like. Here it's a city NGO that we are working on. Then here we have the coronal view, sagittal view, and the axial view. And here's the 3D volume rendering of data set that we are working on. So first and foremost important thing is whenever we are working on such data set, what we can do is let me just copy this DICOM so we can later on see the difference between the original DICOM that we are having and what DICOM that we have obtained after we have used certain filtering result. Since we are dealing with optimization, so we can go into the recursive Gaussian, selecting out a value as 2, and we need to select which we need to select as active. So we will go over here, target copy of DICOM, and whenever we will click on apply, it will take some amount of time. Once it is done, we can check out the results. So you can see the number of noises that have been reduced are by a significant margin. This was the data set that we were having. A lot of noises were present, a lot of small artifacts were present, and this is the result that we have obtained after using a recursive Gaussian filter. So there might be a question that it may also uh, it may also result in loss of features. So that might be true. But what we can do is 1 to 3 grayscale value, 1 to 3 pixelated value in recursive Gaussian is recommended for medical use case. So a value between 1 1.5 is generally fine while we are processing. So for example, if I'll just type in a value as 1.5, and since we are using a cubic and isotropic, so it will take the same strength in all the 3 directions. Once we redo this, we just click on apply, and it carries out our noise removal. So we can see certain noise are removed. So a value between 1 and 1.5 can be generally used for. Now, what we need to do is whenever we are dealing with such data set is, uh, if we need to focus on the heart specific data set, currently the memory data set that is required is around 280 MB. So it's quite significant amount of memory requirement, because once we will be starting the mask creation, the memory would be further increasing and it will increase the load on the system that we are using for. So the first and foremost thing that we can do is we can crop this particular data set. So these are all the optimization techniques that we can use to work on the data. So we can see this is just an empty volume that was being occupied. Sorry. So this was the vacuum spacing that it was occupied. And here we can directly eliminate the particular spacing. We can also do the same directly from the 3D view or the 2D view, whichever is preferred. Here we can zoom in the range and we can just crop down the particular data set directly. Here, one more thing can be done. We can just zoom in the result and we can further crop the data set over here. And whenever we are cropping the data set, just keep in mind that we don't neglect any part that is important. So once it is done, we will be just clicking on apply. Here we can select the frames as active frame and all frames. So whenever we are cropping in all frames, so whichever time offset that value that we are carrying on, it will further apply the particular cropping in all frames at once. Once it is done, we have this crop data set that is obtained for, since it's a 4D image data set, we can also use a sine mode and we can see the particular heart beating in this particular view. Since whenever we had applied the recursive portion, so here we can see the noises are still present in the other data set, because currently the particular data set that it is visualizing is this one. So what I'll do is, sorry. We'll just go over here and now we can see the other time frames over which the data set is observed. Whenever we are applying the particular filter, we need to also see that corresponding to which particular time frame we have applied for the filter. So since we had used it for the 0th frame, so that's why the noises got removed in the 0th frame, but it wasn't applied in the other frames that were used for. So for doing in the similar other frames, we can again go over here. Now selecting target frame as all the particular frames, clicking on apply. And now we can see the particular recursive Gaussian has been applied in all the frames at once. So whenever we are working on any operation, we need to select a particular active frame or all frame. As default, it is always selected as an active frame. So we can go over here and we can change it to all frames, and now whatever operations that we whatever segmentation operation that we would be doing will be occupied in all frames at once. Then we also have a resampling option. So we have the option to either upsample or downsample the image dataset. Upsample in the case where the dataset is not actually properly recognizable, and we are facing very difficulty in identifying the particular boundary segmented region. So in that particular samples, we can do the upsampling. So to do the upsampling, we just need to half down the values. So 7 and 0.35. So we can see the changes that it is showing. So current pixel related value is 355, 331, and 267. So what is this 335, 355, 331, and 367? So it's the particular slices of image that we are having. So 331 is in the coronal views, then the particular 266 is 267 is in the axial view, and the particular 355 in the sagittal view. Whenever we will be doing upsampling, it will just double down the value. So whenever we will click on apply. Now, for what we had done is we had placed on the slice thickness, and thus if we need to have a proper representation between the dataset, that too can be performed. Here, whenever we will apply this operation, the dataset memory size will increase by a significant value. So it's generally recommended to use it in a single series, because whenever we will use it on series at once, it may sometimes cause some issue. So we can see that now the whole data set has been just distributed out thoroughly across the different regions. Now we can further move on to doing the segmentation. Before that, we also have further aligning tools. So if we have a tilted data set along any axis, so that too can be corrected out. We can select a method as align with the particular vector with axis. We can pick the particular points, for example, this point, and whenever we'll say another point, so we can tilt by whichever extent that we require. We can also specify angle. So if we need to do any specific rotation of the image data set along any axis, that too can be carried out. Now coming on to the threshold based segmentation. Here we can use two methods of segmentation whenever we are considering the semi-automated segmentation. So we can use the threshold based segmentation, or we can also rely on the background flood fill one. Here, coming on to the threshold based, it will provide us a decent approach. Once it is done, we can select out the threshold range. We can also select out the profile line to further map out the grayscale variation. So for example, if I select this point and this point, so it has taken a profile line of around 41 mm, and it has shown me the particular grayscale variation between these points. So the lowest most grayscale being around 222 and uppermost being around 670. So this way we can, whenever we will select between these 2 points, whole area that is lying between these 2 points will get connected. We need to also click on this fill cavities in resulting marks to fill all the cavities that are occupying a voxel count between 10 or below, because that may be just due to the artifact effect. And we can also click on this, only keep the largest resulting island. So whatever small islands, so these repeat part that are being visible, so these are disconnected from the mainland, so it will get removed out when we will click on this, only keep the largest resulting island. Once it is done, I'll just click on apply. Since it is working on all frames, it takes time. It takes around 2 to 3 minutes for a single frame. The task gets completed in around 30 seconds. So the time difference is significantly there when we are working with a 4D image data set as compared to a 3D image data set that we are working on. Yes. So once it is done, since we have used it for all the particular target frames, whenever we will be working on this frame toolbox, we can check the segmented result corresponding to each and every time frame, whichever is required for. And once the segmentation is completed, we first need to click on this generate a fast preview to observe out the results more clearly. So it will just take some more amount of time to further use the filtering option to remove out the resulting element. Meanwhile, I have another data set. Here it's an EMRI data set that we have used the automated segmentation for. And while working on this auto segmentation, the particular knee got segregated out into different tibia, patella, fibula, femur cartilage, and we can isolate each and every part out. So this way, we do have support for a MRI data set too. So for example, if we need to isolate any specific model out, we can do it like this and then further work on. Here, there are certain more filters. So if we are observing that the particular surface is not that proper and there are certain artifacts that are missing and it's basically looking too pixelated, what we can do is we can go in the image processing section. Here we can apply for a local surface correction, a value of around 0.8 searching radius and smoothing radius around 1 would be fine for this. Well, whatever target that we need to select, we need to select it over here. We need to set it as active. Once it is done, clicking on apply will further locally surface correct any part that we are working on. Once it's done, it hardly takes some amount of time for it to be processed. We need, whenever we are working on any operation, it will always show once the operation is completed as the auto date. So to have it generated at precise value, so we need to always click on generate a fast preview, and this way better surface quality results can be obtained. And once it is done, we need to next move on to any smoothing filter option to further smooth out the particular part out and get the most accurate result out of it. Once it's done, we can also rely on a smart paint tool to further enhance any part that we're working. And whenever we are working with such parts, we can also at any time enable this background volume rendering. And once the background volume rendering is enabled, we can overlap it with the particular segmented part that we have offset for. So to do that, we can just select the particular mask. Once the mask is selected, we can see uh, that it's almost marking up the particular volume rendering of dataset. At some point, it's also having some region to be marked out. So we can at any point remove this out. So it's some artifact that due to which the particular defect got created. So we can anytime remove it out using a 3D editing option. So we will just go over here in the 3D editing, simple 3D editing, and we can easily apply for a NASA operation to remove this particular part out. So even if we need to disconnect any part, that too can be done. And once it is done, we can select another operation like local surface correction and followed by an erode and close, and it will further refine my existing region. So once it is done, it these tasks generally take around every tool that we have takes around 1 to 2 minutes. It also depends on the data set that we are working on. Uh, what's the data set size that we are working on? So these are all the particular values that we need to take consideration for. The particular segmentation is still running since, for example, if for a single time frame, it requires around 2 minutes. So these are around 20 time frames for which we are observing the data for. So it will take around 40 minutes of time to do the segmentation. So general segmentation time is around 30 seconds for a single time frame. So considering that particular part out, so it takes around 5 to 10 minutes to do the particular segmentation across all the time frames at once. Meanwhile, this particular surface got local surface corrected. Once it is done, we can further use other operations like erode followed by a close. And one of the most advantageous thing that we have in Simpleware, for example, if we aren't familiar with the morphological operations like erode close, how it would work. So we can anytime click on this question mark sign and we can go open it in a longer view and we can see how after applying the operation our results would look. So erode will shrink that down, then we have the dilate one that will increase the particular dilation, so it will increase the grayscale range along the extent. Then we have the open and close tool. So we have a graphically integrated uh, guide for that, how we can use the tools and how the results will change once we have applied the different sets of operation. So here we also have a 3D rep. For example, if we are if we need to do proper interpolation between the slices, this way a 3D interpolation tool can also work for. So this is how it basically works around basic image segmentation techniques. These are the basics of Scan IP. I haven't focused much on the auto segmentation part since this webinar was specifically focused for how to optimize the particular results. Then for example, if I am applying, let me take the same knee MRI segmentation and do a manual segmentation for it. So before that, what we can do is we also have got one more new feature included in this latest release. Here we can always create a new folder, and once the new folder is created, so it helps us to basically label each and every part out and further clear out our GUI, whichever part that we're working for. Once I drag and drop it in auto segmentation, I'll just toggle the visibility of the whole parts at once. And now I'll get an empty mask tab to be working on. Whenever we are working with a manual segmentation, we can go in the background flood fill. Here we have a fixed threshold based operation. Here we can select the threshold. And now whichever point that we will be clicking, that will be carrying the particular range in this threshold will get painted. Better approach for soft issues is to use a seed point based approach. So here we set a delta set can be selected around 25, 20, any value can be selected. So what it does is, for example, whenever I'm hovering on any point, so it tells me the coordinates, the x, y, and z coordinate followed by the grayscale range. So for this particular point, the particular grayscale range is 1129. So what this particular tool, the background flood filler seed point operation would do is, it will take a grayscale value into consideration right from 1104 to all the way to 1149. And once it is done, if I select on this part, uh, sorry, what I'll do is I'll create a new mask, and whenever I'll click on any point, whichever is lying in this particular grayscale range. So it was considered 1129, so a value between 1104 to 1149. So since we have taken minus 25 to plus 20, will get painted. But still, many of you might have questioned that it has only painted a certain region, and we are still to fully model the particular part out. So to cover that part, what we need to do is we need to select the merge operation, and clicking on merge operation, it's similar to be using a region growing operation. We can easily uh, identify the different regions, and we can uh, ultimately develop the particular model out of it. It takes some amount of time, but still, it's better approach than to use a paint with threshold tool or a normal threshold, which will also carry a nearby region. So we can also use our region growing operation. So here we will select a number of, so we need to select the output as a merge operation, and just cancel this particular segmentation out. So the system's lagging a bit. Let me just reopen the data set. For that, let me see if the segmentation is complete. It's yet to complete, so I'll just cancel this operation. Yeah, so here we had to use a region growing for this particular mask that we were using. So what we need to do is we need to select it as an active mask, and once it is selected as active mask, we need to select the output as merge to merge with the existing mask that we are having. So this way it will start merging the particular parts out, and it will start to vision grow the particular part out on the basis of nearby grayscale range. This is the best way to easily model that part out. And once we have a distinguished structure, we can use a 3D wrap option or even a bone filling option to further solidify the particular part that we are working. So this being a femur, so we can easily identify the particular femur. And once the particular femur has been loaded, we can go to the bone filling and we can apply the bone filling operation to further solidify the particular part that we are working for. Once this particular segmentation is done, the bone filling has been done. The bone filling operation generally takes 2 to 3 minutes for the processing. You can further move out the result. Meanwhile, this particular segmentation got completed across all the time frames. We can just generate a fast preview over here. And once it is done, we can select out the results. We can see across all the particular time frames how the segmented result would look like. All the nearby small rib cages that was to be seen got removed. Once it is done, so what we were earlier seeing in the background volume rendering now can be directly seen after the segmentation has been performed for. It generally also there's a dedicated GPU requirement to use this background volume rendering or to use auto segmentation. So there's a dedicated GPU requirement, and the minimum recommended system settings is around 8 GB of GPUs. Any RTX 3060 of 3060 or above is basically recommended to run the software efficiently. So will take some more amount of time for it to process. So what it is doing is basically it is calculating the 3D object contours corresponding to each and every time frames. Once it is done calculating the 3D object contours across all the particular 20 time frames, we will be getting a particular cine box of the same. We see, yeah, so the bone filling operation got completed and we got a somewhat solidified structure. So this is almost similar to the surface that we were working on. Still there are gaps that are present, so we can anyway go a smart paint tool and further fill out the region. So I'll just increase the brush size too. So this are the various approaches that we can use to further enhance whatever workflow that we're working on. And then we can again go to a bone filling and we can solidify the part. So there are multiple options that we need to use. We can't rely on any specific operation that uh, what if we require only threshold. So that's not the usual case. We need to use a smart paint also, threshold also, bone filling also, local surface correction. And whenever we will be using multiple sets of operation, we will be getting the best accurate result in the least time that we are computing for. It's still getting completed. GPU is causing some issue for the dataset to be loaded. So it's taking some time. So edit what I can do is I can instead show corresponding to each and every time frame how the segmented output would look like. And this is, for example, if we need to check for systolic phase or diastolic phase, so the time frame can be selected accordingly, and we can further move out this result. Apart from this, if we need to directly check the internal features, we can anytime enable the 3D clipping and we can check for the features. Similarly, the 3D clipping can also be used to select out the frame and cut it accordingly. So whenever we are using it, we can directly go inside the features. We can directly go inside the dataset to see the internal features. like this particular model can be created in the least amount of time. So this is the basics of Simpleware, how various tools can be used to further optimize the particular results that we are working on. So anyone has any queries till now? I'm just opening the session for question and answer. You can ask your queries. Also, I'm sharing my contact details. So further, if anyone wants to send the queries over WhatsApp or over email, so you can just send it from here. I'm also typing the same chat box. Yeah, so I have shared my details in the chat box. Please, anyone with any queries, you can just ask. No queries, anyone? So there's one. Whenever I upload DICOM images, I'm only able to work with phones. I can't be able to work with other organs. So yeah, so this is one such query that many of our users face to identify different structures. Whenever we are working with a DICOM image, for example, CTNG is specifically meant to highlight the contrast value for the particular hard part out, apart from the remaining parts. So what we have is we can do is we can use a multi-level auto segmentation in that case. How to do that? It's very simple. Let me open another dataset. These are huge datasets to show how a multi-level auto segmentation would work. So I'll just open a normal pelvis dataset. I'll just open a pelvis dataset. So this was the difference that I was telling. If we are opening a single series dataset, it takes around 10 seconds for the dataset to be loaded. If we are taking a DICOM directory, it will take more amount of time. So this is a very good question, Mr. how to basically segment out the different results that are being presented. So I'm just presenting my screen. Please let me know if it's visible. Yeah, I hope now it's visible. So whenever we need to identify different parts within a single set of data set, and if we are not very clear how to do that, what we can do is in this advanced tool option, we have an option of multi-level auto segmentation. Here in the multi-level auto segmentation, for example, if I am defining 5, so what it will do is it will identify the grayscale range, and according to the grayscale range, it will create 5 separate masks for me, and then corresponding to the shift in the grayscale value, each and every part can be identified out. So for example, if I am only considering the yellow and purple region that is considered for. So I'll just apply a Boolean operation to combine it at 1 union with also 5. So what we can do is we can use a ORTSO based approach to further identify the region. So it's a basic approach wherein we can identify the different regions. So a muscular region can be identified out, segregated out from a orthopedic region, skin layer can be found out. So this is one such way that it can be done. Also, there is one more option that we can use is if we need not to use this one, we can work on a peak to peak basis in the threshold value. So we go in the threshold tab. So you can see there are different peaks to be observed for. So if I am taking a bone, for example, till this, I'll just delete this particular existing part out. Clicking on this, Then if I take from this peak to the value that I selected, we'll getting a different region. And for example, if we need to check out the airbase, then this time, then we'll further reduce down over here, checking another grayscale range, setting it up. So this way, different regions can be identified on the basis of peak range. And once it is done, we can further move at the last part to carry out the distant region. So for example, earlier in the same dataset, the distant region wasn't very visible. Now what we have done, we have segregated out it from the rest of part. Once it is done, I'll just isolate this part to have a proper visualization of the same. So using a mass split fill approach, I'll segregate it out from the skin, outer skin region that it was computing for. So better approach is to just cut out the plane. Yeah. So like this, different regions can be identified. So it was the same CT data set. Here the bladder can be identified, intestine can be identified. Here the particular bone region could be identified. So this way, using a threshold-based approach, we can segregate out different regions. Can we get CT DICOM dataset for testing? Yes, sir. We do have some in the sample dataset that can be shared for. How you can just drop in a message in at my WhatsApp number. I will respond to you over there. I hope, ma'am, your query was cleared. Then, even if your query is not clear, you can still contact me. I'll surely help you out how to distinguish different regions. Any more questions, anyone? So I don't think there are any further questions. I'll just switching off this session for now. We'll meet in the next session whenever it's going to be organized. We'll inform you over LinkedIn. You can follow us over LinkedIn. And thanks everyone for joining. Have a great day.